Hi everyone, I'm Dr. Surjit Singh. Today we'll talk about the Leetcode problem, count of smaller numbers after self. Let us begin. We are given an array of numbers. For each number, we are to count the numbers present after it that are less than it. In this problem, we have to compare all the numbers with each other to get the final solution. Double loop time complexity is of the order of n squared. So merge sort comes to our mind, in which we compare the numbers in the list with each other once for every pair. Consider a list of 7 numbers. We initialize an array for saving counts. In merge sort, we need to swap numbers with each other, but we require the original indices to find the counts of every number. So we define an array of tuples in which we save the numbers and their original positions. During sorting, the original positions will move along with the number. Sorting requires two functions, merge sort and merge. In the first call of the merge sort, we use the entire range of nums. We will sort with respect to the zeroth component of the tuples which contain the actual number. In the recursive function merge sort, the initial values of left and right pointers are 0 and 7. In the range left to right, we will sort elements between left and right minus 1. Let us first discuss the edge cases in this recursive function. If there are 1 or 0 elements in the range, we return without doing anything. For a larger range, we find the mid position, which divides it into two partitions. Left partition has 3 elements while right has 4. We sort them separately in two recursive calls of this function. Merge sort of left partition gives this arrangement, while the same on the right partition gives this. Left partition has 0, 1 and 2 positions, while right partition has 3, 4, 5 and 6 positions. We then merge the two partitions into one list. For this, we pass the three pointers left, mid and right to the merge function, in which we define two new pointers I and j at the beginning of the two partitions and a list named merged. We start a loop that runs till neither of the two partitions reach its end. We compare the elements at position I and j, append a copy of the smaller of the two to merged, and move its pointer. In case of equal values, left partition moves. Next 5 iterations are these. Now that one of the partitions has exhausted, we come out of the loop. As I is less than mid, it means that some elements of left partition are pending, so in a loop we append them one by one to merged. Next we replace all the elements of merged list one by one back to array. If right partition elements are pending, we need not append them to the merged list because finally they will go back to the array at the same positions. Merge function ends and the entire array is now sorted. Now we need to make entries in counts. So let us add this statement in the function merge and its copy at another place. These statements operate when I moves and not when j moves. To understand these statements, let us dry run the program from the beginning. In the first call of merge sort, left and right are 0 and 7. The logic behind these two new statements is as follows. During merging of the two partitions, whenever an element of left partition crosses an element of right partition, it means that it had a smaller element present on its right. In such a case, we increase its count by 1 for each element it crosses. We start with initial unsorted array. In the next call, we start with the sorting of the left partition whose left and right pointers are 0 and 3, so mid becomes 1. Its left partition is the edge case. Its right partition makes another call to the recursive function whose two partitions are of single element each, so we directly start merging them. Element at I is smaller. It will move first. At the moment, j minus mid is 0, so there is no change in result. We append 1 to merged and move I. Left partition is exhausted. There is no use merging residual part of right partition. We restore merged list back to the original array. This call ends. We have now sorted both the partitions of previous call. We now merge them. In the first two iterations, j moves and we come out of loop. 5 is the residual part of the left partition. J minus mid is 2. It means that when we append 5 to merged, two entries of right partition are already present there, which will be crossed by 5. So we add 2 in counts at the position of this 5. We now append 5 to merged and move I. The two numbers crossed by 5 are 1 at position 1 and 2 at position 2 in nums. It remains within the range of 0 to 3. In a later step, it will cross 4 more elements of nums when partitions 0 to 3 and 3 to 7 of the range 0 to 7 will merge. Now we restore merged list in the array. With this, we have sorted the left partition of previous call. We now sort its right partition for which left and right are 3 and 7. In the next call, left and right are 3 and 5. Both sides are edge cases, so let us merge them. 1 is less than 3 and it moves first. At this time, j minus mid is 0. It means that in the range 3 to 5, no number less than 1 is present in the right partition. We append 1 to merged and left partition ends. There is no need to append residual part of right partition. We restore merged at left. Now we take up the right partition of previous call for which left and right are 5 and 7. Both partitions are edge cases, so we merge them. 1 moves first, j comes out of range. Now is the time to append 2 to merged. One element of right partition is already present in merged because j minus mid is 1. We raise count of 2 at position 5 of nums by 1 and append 2 to merged. Now we restore merged at positions left onwards. We have sorted both partitions of previous call. Now we start merging them. Left partition moves first, but merged was empty, so no effect on counts. Then 1 and 2 move from right and right partition exhausts. We will process residual part of left. J minus mid is 2. It means that two elements of right partition are present in merged. We raise count of 3 by 2 and append it to merged. We now restore merged and this call is also over. The two sides are separately sorted and no element has crossed sides. Left partition elements are from the original positions 0, 1 and 2, while right partition elements are from 3, 4, 5 and 6. The two partitions will now merge with each other. I and j are at the beginning of the two partitions. Pointer I moves after we append it to merged. J minus mid is 0, so no change in any result. J moves in the next two iterations. Next turn is for the left partition. Merged has two entries from right partition. we increase count of 2 at position 2 by 2. We append 2 to merged and move pointer I further. J moves to the end in next 2 iterations. Out of 6 entries now in merged, 4 are from right partition. 5 is the residual element in left partition. We increase count of 5 by 4. Append 5 to merged and increase I by 1. In the end, we replace array with merged. All calls of merge sort end. We return counts as the solution. Time complexity is due to merge sort, which is of the order of n log n. The 3 arrays used are of length n, which becomes the space complexity. Thank you for your time. I hope you enjoyed the video. Please stay tuned for more such interesting problems.